testing. Here you can see the learning objectives of this lesson. You should understand the concepts of black box and white box test, observability, controllability, testing. We should understand what a unit test is used and how it is constructed. Similarly, how an integration test is constructed and how acceptance test is constructed are the other objectives of this lesson. Okay, there is a common framework that is discussed in the textbook as well as in other materials. Test V, what we call test V. Actually, when we start our project and process what the customer need, specify the requirements, we have to start testing. We have to keep testing in our mind and develop specifications, requirements accordingly. Here in test B, you can see on the left-hand side the development phase, and on the right-hand side the testing phase. And each of the stage in development phase corresponds to testing stage on the right-hand side. For example, when we are developing requirements, we have to think about acceptance test because the requirements are somehow derived from the customer need, either as engineering requirements or marketing requirements. And usually, when we talk about acceptance test, we somehow use or refer to engineering requirements. Once we start system design, then the corresponding test phase is integration test. In construction, it corresponds to unit test. And at the bottom here, you can see debugging, which is about component or model level problem identification and solving. So let's see next black box and white box test. On the right-hand side, you can see two system operation. There is an input and output for each of this. At the bottom, you can see the details of the system is known. On the other end, there's a question mark in the black box, so-called black box test. So in black box test, we do not have any knowledge about what is inside them. And we have only inputs and outputs. We have some connectors, let's say interfaces or form of input and output. And we simply test this system without knowing anything about the internal structure of the system. So usually we are given some range of values for the inputs and values for the output. And typically the inputs could be a typical value, a boundary value, or extra value, or an invalid value. We have to try the system by applying all this type of values at the input and try to understand how the system responds to this inputs. So simply we change the input and observe the output for some expected values. We do not know about the content or the structure, internal structure of the system. On the other hand, for white box test, we have knowledge about the details of the system. We know the structure, the architecture of the system. We might expect when the system might give some faults at the output. We know how, or we can expect how the system may respond to some typical value or boundary value or external value. And what happens when we apply an illegal value or invalid value to the system. So we simply try to examine whether the system works correctly for those inputs. And usually we know the expected outcomes, and we try to impose the system to make some errors, actually. Okay, let's see engineering design and how it is related to controllability, observability, and testability. Actually, when we start a design, a system design, we have some goals, usually based on needs and requirements. We have also some other goals. These are testability, controllability, and observability. Testability, it's about the failure of the system, how it fails, or under which conditions it fails. And the testability is about how to detect the failures, how to locate the failure. We have to know it. We have to identify failures. We have to locate the failures. If we couldn't test, then the system is not a testable system. Controllability. Any node of the system can be set to a desired or prescribed value, and usually black box, as we expected, does not have controllability, while white box somehow may have ability. And finally, observability. If any node of the system can be measured, then that's observable. As we expected, black box testing of observability, while white box testing may have some higher observability. When we want to develop the test system, we usually deal with test cases. We develop test cases, and usually we have to develop test cases from very beginning of the design, when we are, as we said earlier, specifying requirements. We start the test cases. We need test cases because test cases define exactly what the model or system has to do. Testing may sometimes prevent over-design. We may, for example, develop a requirement, but if it is not possible to test that requirement, then we have something wrong there. So we have to think about it. If there is a system that cannot be tested, then it's an exaggerated system. It could not be. So to prevent over-design, testing, so test cases are quite important. Test cases motivate the developers by providing some immediate feedback. So we may sometimes redesign some part of the system. So quite useful design stage. They may also force designers to think about some extreme cases. So if you play with any meter and try to see how system responds for some extreme or invalid values, then you have to think about design again. The test cases are quite important for documentation, as the design process usually time. We have to write down everything, and when we prepare a test case, then document that, and then it could be used during the design process. Usually, test cases somehow enforce the designer consider the design of model before building that. That's a very common mistake. We always, or most of us, start simply design of a model or building a model before designing a model on a tool. So test cases somehow force us to consider the design before building a system or some part. So here you can see test case properties. Test cases should be accurate, economical, limited in complexity, repeatable, appropriate, traceable, and self-cleaning. So we can somehow understand what each of these is first, but we can briefly talk about that. Accuracy, test should check what is supposed to do, and it should have an intention, it should have a specific goal. It should be performed with minimal steps and should be 10 to 15 steps. And, it should be performed by anyone. I mean, not dependent on who is going to test it. Everything should be clear enough so that perform that test. This appropriateness is important. Many of the systems, there may be many system design or system development. There may be many people working for the project, and sometimes we may assign testing to individuals who may not have experience. So we have to assign, or test case should be clear enough such that any individual can perform it. Each test case somehow refers to requirements. So as we said earlier, when we are developing requirements, we simply think about the tests. And when we apply something on the system while we are testing, then the system should be returned to the test state after the test is complete. So self-cleaning is important for test cases. One of the components or wording is quite common in testing, stop. Stop is actually a device or a simulator, usually, that mimics a subsystem or a model. So that's a kind of placeholder for the functionality of a system. On the circuit shown below, you see on the left-hand side, we have a function generator and resistor and capacitor block. This block is connected to the JT amplifier. This is very common. And at on the right-hand side, you can see a load. So we simply generate a signal and then apply it and then apply that reload. You can imagine that there is a sound generated on the left-hand side and fire, and on the right-hand side we may have a speaker. So here we can somehow simulate function generator and RC components as a block using a device or a software. And so this is simply called a stub. So we can replace the system by a simulator, which functions as a stub. It gives exactly the same values that this block produces. So without using a function generator and RC element pair, we can generate exactly the same signals applied to this. In many of the simulators design tools, we have such blocks. We simply replace full system or subsystem by a simple block. In software, this could be just about calling a function. Okay, let's go back to test V. We see on the left-hand side development, on the right-hand side stack. And we here start with the bottom debugging. That is, as we said, about components. The lowest level of testing. And next we have unit test. Usually unit is consisting of some components, units, and at the integration test we have some tools here consisting of units, and then acceptance tests where we have full system consisting of modules or subsystems. So we go through debugging, unit test, integration test, and test. So let's start with debugging. You may know, you are familiar with bug. If a system doesn't function as expected, then there is something wrong, and this is called bug. Debugging is just about identification of root cause of the problem, then correcting that. Right? So there is a procedure for debugging: observe the problem, form a hypothesis, and conduct experiments, and repeat this 3 steps. So we simply first observe the problem, what the problem is, and try to understand how it occurs under different operating conditions. And then, based on this problem, we can form a hypothesis, and then perform some experiments to confirm or eliminate hypothesized source of the problem. If it confirms, so we can eliminate the problem, then we debug the system. If it doesn't work, then we go back to the first stage and then observe the problem again under different conditions, and then form another hypothesis, and then conduct the experiment. So we iteratively follow this procedure, repeat this until we resolve the problem and complete the debugging. Unit test is the next stage. That's complete test of the functionality of a module or a system or subsystem in isolation. So we take a unit, isolate it from the system, and then we have a set of test cases here, and we try to understand the functionality of the model or subsystem. The test cases should be traceable to the detailed design as we expected. Each test case should simply examine single unit of functionality to some specification, and test cases should be written with the express of intent of uncovering defects. So simply, unit test is a set of test cases. So we have to know how to develop, how to write for unit testing. And let's see test cases. There are three types of test cases: matrix test cases, step-by-step test cases, and automated scripts. Majority of the systems in electronics and computer engineering has been using automated scripts, but in some hardware, we still need to use matrix test cases. What is a matrix test case? It's best suited case where the inputs submitted are structurally the same and differ only in their values. So if we are given a system and if we simply vary the voltage at the input, and that's going to be a matrix test case, because we only change the values of the voltage. Test is the same. On the other hand, for step-by-step test cases, here there may be a complex sequence of steps. There is no simple structure. There is a single value or single one here. There may be many, and we have to determine the sequence of steps. Automated scripts, as we said earlier, a sequence of commands provided to unit under test without user intervention. So we simply plan a system, we develop a system. We do not interfere with the testing here. The system tests the unit under test, UUT, without any user intervention. This type of test case may be applied to integration and acceptance test as well. Here you can see a matrix text for thermometer. We have already studied the thermometer design, digital thermometer design, and here you can see the sections here: test writer, test case number, test ID number, type, description, tester information. Here you can see that the test writer and tester are different people. In practice, in many of the systems or in many of the projects, test writer, tester, designer, developer, all should be different peoples, especially designer and tester or test writer should be different groups or different people. Here, the test case is ADC function test. Verify conversion range and clock frequency. Output goes to 0 in presence of null clock. So on the test here setup, we see the test 1 and 5. So 0 volt and 2 volt are applied with clock frequency 0, and the expected outcome in decimal given here. So the tester is simply the click here, pass or fail or not available, and if he or she wants, then insert some comments here, and there should be an overall test result that should be reported by the tester. Here you can see a step by step test. Again, we have test writer here. And the difference here, as you can see at the bottom, the steps from 1 to 6, and there is no simply a voltage variation we apply here. There are different cases, states in here, and we simply inspect whether the system, which is a vending machine here, whether the system changed the state or not. So in projects, you are supposed to develop such test cases. Integration testing. Usually we develop integration tests during the level 1 design. And we simply make sure that the requirements are met. And usually we think about favor of subsystem or modules here, not the whole system, but subsystem and modules. We simply examine the response of the subsystem to extreme values, for example. The test cases in integration tests should be traceable to high-level design, and they should be written on the basis of the characteristics of the design architecture. So when we are writing integration tests, these could be the questions that we have to ask. What are the different paths of execution through the system? Are all modules exercised at least once during integration? Have all the interface signals been tested? Have all the interface modes been exercised? Does the system process information at the required rate and meet the timing requirements? So answering those questions could help us to develop integration tests. Finally, we have acceptance testing. That is, as we can understand from the name, about the customer. We have to face with the customer and ask the customer whether the system that we have developed and implemented meet the requirements of the customer. Usually there should be some formal documents, legal documents that we have agreed on, and they should be somehow written in accordance with the requirements. They should be traceable. And then when we say requirement, we have to think about the core attributes of a good requirement: abstract, verifiable, traceable, and unambiguous. So the testing acceptance stage, the testing should be defined such that all these 4 attributes should be met. The system do what it's supposed to do. You have to make sure. There should be objective pass and failure. We have to agree with the customer criteria for pass or fail. We have to target the need of the project, and everybody should be up on the test here. Here you can see an example. That's an autonomous robot. There is a robot here, as you can see. I try to illustrate this. There's a wall, and this autonomous robot is expected to travel next to the wall within 12 to 13 centimeters from the wall over a distance of 3 meters. So here you can see the engineering requirements for this. The robot center must stay within 12 to 18 centimeters of the wall over 90% of the course. So 90%. while traveling parallel to a wall over a 3-meter course. So you see, it seems to be quite easy. We measure 12 to 18 centimeters, but when we say 90% of the course, so when we move from here to here, 3 meters, so 90% of the course, this should be within 12 to 18 centimeters. So that's not easy to measure, right? So we have to be careful when we are writing this requirements. Robot's heading should never deviate no more than 10 degrees from the wall's axis. So from 10 degrees to the left, while traveling parallel to a straight wall over a 3-meter course. So when we want to develop the acceptance test, so there should be this type of test case, yeah? Test writer, test case name, robot acceptance test number 1, text the engineer requirement. Here is the first engineer. On the right-hand side, you can see test ID and type, white box or black box. Hardware version, the name of the tester, date, time, and the setup is simply completed. Robot should be fully charged and placed on 3-meter test track. Write a program to monitor the robot's position from the wall. So you see, that's not about the development of the robot itself. Here, we are writing a program to monitor the robot's position from the wall. Okay? Put robot on test track and run the test and download the data. Plot test data in a spreadsheet program. Okay, so here is the expected result. So we have to here simply test whether this requirement is met or not.